Okay, hello everyone. It's my big pleasure to introduce Andrei Okounkov from University of Columbia, who is now in Tokyo. And Andrei will speak about the unramified Eisenstein spectrum. Thank you.
Thank you so much. It's a great honor and pleasure to be speaking at the seminar. It proves it's not just Zoom and gloom. There's also good things about Zoom that really can connect people from all different continents and bring people together from many different countries. I realize that from some of you this may be an inconvenient time of the day, and I appreciate you being tuned into this talk. It's rather late here in Tokyo. It's early in Europe, and it's really weird hour in North America. But anyway, so I'm going to report on our recent and ongoing work with David, who's here with us too, and this concerns what's well, the title is the unramified Eisenstein spectrum, and what is this about? And it's actually one of the central questions in the theory of automorphic forms is to describe there's a certain space, and we would like to describe a spectrum of certain operators on the space. And so I'll first introduce the space over a few slides. And the short definition is the following: you take a split reductive group over a global field, and the group will be denoted G and the field F. And then we take the ring of adeles of that global field F denoted A. And then we take this double quotient called BUN, and for the reasons that I'll explain in a second, it's on the one side you mod out by the maximal compact subgroup in the adelic group, and on the other side you mod out by discrete group, which is your group of the field where field is embedded diagonally in the adeles. And so this is a quotient, and it has a canonical measure, which is in fact finite. Well, finite if the group is semi-simple. Then the question is to describe the L2 on that space. But maybe this definition may be a little too abstract. Maybe let's see what it says in concrete examples. Like for example, if our field are rational numbers and the group is GLN, then the above quotient will reduce to the following double quotient. You take the real points of GLN, and on the one side you mod out by the orthogonal group, and on the other side you mod out by the GLN Z, the matrices with integer coefficients. And this double quotient you can identify with the space of lattices modulo the isometry. And how does you identify it? Well, of course, if you can pick a basis of a lattice that is defined uniquely up to an action of GLN Z, and so this is GLN. The quotient on the one side is just the space of lattices, and the quotient. And when you take the quotient on the other side of the orthogonal group, you consider the space of lattices up to isometry. And what are the operators that we would like to consider? Are well, we'll call them Hecke operators for short, because it's some large commutative algebra of operators. And what are there in this instance? Well, first there are some differential operators, and that come from if you look at this at the space of ln mod O, that is so for the lattice, that is the space of prime matrices, so the space of positive definite symmetric matrices, and it's a symmetric space, and there are invariant differential operators on that space. This is the Archimedean part of the Hecke algebra, and also there are classical Hecke operators that come from the fact that if you have a function defined on lattices, you can sum it over short exact sequence of the form which I explained, which I have on my slides here, where you fix so if you have a lattice gamma and you fix the isomorphism type of the quotient gamma mod gamma prime, then you have finitely many choices for this gamma prime, and you sum over all. So that's the Hecke operators, and so that's one example. And then another example is why. So maybe that's the example why this is called BUN. Is that another kind of global field is the field of functions on a curve, which on a curve over a finite field, which will be denoted small ball blackboard K. And then the maximal compact subgroup in this case has a very concrete realization as just your group G with the entries in the ring of integral adels. And so then this you get the double quotient where in the middle you have the G of the adels, and on the other one side you take G of the integral adels. On the other side you take the G of the field, and it's well known that this double quotient is a stack. Those are the K points of the stack of bundles of the G bundles of the group C. So concretely for the group GLN, this would be the stack of vector bundles of rank n on your curve. And so for vector bundles, the Hickey operators may be defined in exactly the same way as they were defined for lattices. Namely, if you have, you can sum over sub-bundles where you fix the isomorphism type of the torsion sheaf V mod V prime. So there'll be a finite sum. And if you have a more general group, then what you're really doing is you fix a point on the curve, and you fix a double coset of the groups that I have here on the slides. And so this is a general prescription of how the Hickey operators operate. And so maybe I'll go backtrack for a second. So they have a space. You have L2 in a certain space of, say, finite measure, and then you have a sequence of a supply of operators which you like to diagonalize. So that's the problem. Like I said, the volume for a semi-simple group, this volume of this space bund is finite, but the space bund is not compact. Like it's not compact already in the simplest possible example, namely for the group of SL2Q. And so, concretely, this is famous. I mean, this is a picture, of course, everybody saw. This is this quotient for SL2. I mean, this is SL. Well, this is bund for SL2Q, and that's the space of unimodular lattices. Has two singular points corresponding to the two lattices with sector automorphism, but also has infinity corresponding to lattices. For lattice runs off to infinity if it starts having a very short vector. And so the space, since the space is non-compact, the spectral of Laplace operator contains various things. It has bound states given by functions that very rapidly decay to infinity, but also has a continuous part that comes from kind of scattering states that come from infinity. And so in general, that spectrum of L2 is some mixture of some continuous and some discrete parts, and so that will be also a feature of the answer we get. And more generally, for instance, if you take this space bund for SL and Q, so those would be the this would be unimodular lattices in Rn modular isometries. Then how do we get that modular figure in the previous slide? We first fix the shortest vector in the lattice and then see where the next shortest vector, I mean the vector, the shortest among those not contained in the span of the first one, where is it located? And that gives this modular figure. And then similarly, you can fix the shortest vector, then look at the next shortest, which is not in the space, and the shortest not in the space of the first one, and so on and so forth. And generalizing the situation with SL2 could be a situation that some of these vectors are really incomparable, so some of these inequalities become really, really dramatic. And so the way to run off to infinity in the space of lattices is we have to put some less signs somewhere where they only have less or equal signs. And so this says that for SL and Q, the infinity is the boundary strata infinity, they're indexed by parabolic subgroups, and that's a general phenomenon. Somehow the non-compactness of the space band is measured by different strata that correspond to parabolic subgroups, and reflecting this as a first step of the spectral decomposition, Langlands in his famous, so many times in this talk I'll be referring to a famous, first was a manuscript of Langlands, and it was finally published. So it's called On the Functional Equation Satisfied by Eisenstein Series. And so so this is really kind of an amazing piece of work that inspired many many people working in the area. Anyway, so there, Langlands himself already established the first piece of decomposition corresponding where this L2 breaks up to kind of according to the various boundary strata, except you have to identify two parabolics if their Levy are conjugates called associated parabolics. And the way to write the corresponding decomposition is to use operators called constant terms. They amount to integrating over unipotent radicals of various parabolics. This for SL2, this would be saying there's one parabolic in the upper, and which would unipotent radical would one interesting. Okay, there are two parabolics and one one interesting one. So that has the unipotent radical of upper matrices or upper unitriangular matrices. And so integrating over this unipotent radical is just this integral that I have here. You integrate your function along in the y coordinate, sorry, in the x coordinate from x of 0 to 1 over the period. And so that's the constant term. And so if you look at various pieces in this decomposition, there each piece corresponds to cusp forms on the levy of the corresponding parabolic. And in particular, the pieces correspond to the group G itself. Those are the cusp forms for the group G. And so the cusp forms for the group G, they're say in this example, they're very mysterious, but this is discrete spectrum. Well, we in this talk interested in the opposite case. We're interested in the what's called Eisenstein spectrum. We're interested in the case where we have the minimal parabolic. So this is the largest boundary stratum, generic boundary stratum. And so we're interested in this decomposition piece. We're interested in the part that corresponds to the minimal parabolic, or the most generic boundary stratum. And this piece we denote by L2 Eisenstein. Okay, that's the space we want to look at. And so where I'm going, yeah. So this is what's in that space. So we have L2 on 1. We broke up into pieces corresponding to parabolics, or Langlands broke it into pieces corresponding to parabolic, and then there is the piece which corresponds to the largest boundary stratum, or the smallest parabolic, and this is the piece called L2 Eisenstein. So what's in that space? Also, Langlands shows that the dense subspace of that space is spanned by functions of the following form. So maybe we'll read it like this. The most important part is here's the summation over cosets of your Borel over your field over well, you have the group over your field divided coset Borel over your field. And so then there's a certain function A of some element where you act by your matrix gamma. Then so what's that piece? That piece is you have a group element, and you can take the Evasive decomposition, which is the unipotent radical, and then the diagonal part, and then the element in the compact subgroup. Unipotent radical of the Borel, U sub B, that's the unipotent radical of the Borel, that there is the diagonal part and the piece in the compact subgroup. So you take that middle piece, that's this A of some element of the group, that's the piece of this Evasive decomposition. Then of this diagonal matrix, that's still an adelic matrix. Of this adelic matrix, you can take the norm, which is so this would be now a diagonal matrix with entries in positive real numbers. So you got so you take, in other words, we're still reading this formula. Maybe I'll give my cursor here. So there's a group element G on which we're going to evaluate the function. Then we act on it on the left by some element gamma in my discrete subgroup, or rather in this coset, because B fixes this function here in question. Then we pick the piece in the Evasive decomposition, this A here. We take its norm, and then becomes a diagonal matrix with positive real entries. And then we pick pick an arbitrary smooth, compactly supported function on diagonal matrices with positive real entries, and we sum over gamma. That's the definition. Okay. But it's convenient since the group of diagonal matrices with positive real entries is a group. It's convenient to use a Mellin transform on this group. And so then if we use Mellin transform on this group, we're going to get the same situation where except now we take a character of this group. So we have lambda. Lambda is a character of the group of diagonal matrices with positive real entries. So it's an element in the dual space to the Lie algebra of this group, because the character of positive reals, if you take positive reals that its characters have maybe called it S, then the character of the S are of the form, T to the S, where T is a generally complex number. So that's so the characters. And so then this is, in other words, you take the exact same sum, but now you use a character, and it's convenient to shift that character by the half sum of positive roots, like usual people always do in representation theory or in automorphic forms. And so now you get a series which actually this is called the Eisenstein series. And the series converges if the real part of lambda is positive, and may be defined for other values of lambda by analytic continuation. This function is an eigenfunction of the Hecke operators, but is never null. So that's the kind of the basic tension here. One can write the eigenfunctions, but they're never null too. But somewhere in the span of this function, there are pieces that enter this spectral decomposition, and this is what we want to determine. We want to determine the spectrum L2. We have which is where this of the subspace, which is the span of the functions of which either I have either on the previous transparency or on this transparency, this have the same span. These functions on my group G, and I'd like to know which one of them are square normalizable, not exactly eigenfunctions, but which enter the spectral decomposition of Hecke operators. Okay, I hope I explained the definition, but it is useful to look at examples. Like, what is it for SL2? For SL2Q, we decided that the space in question, the space of lattice, is up to isometry. And then what is this function? What is this mysterious function? Well, not mysterious. What is, if you unravel definitions, what is that sum going to be? So first of all, it's going to be a sum over primitive vectors in your lattice, and the value of this norm of this distinctive norm of A of something, that would be just the norm of that vector. And so you summing over primitive vectors of your lattice, and you sum 1 over their norm raised to the power lambda plus 1. That's this. Another way to think about the sum is that a primitive vector in your lattice is the same as a rational point in P1, which is in the case, this is the flag variety in the case of, this is the flag variety G mod B in the case of SL2. And so this is, if you take a rational point in P1 and determines a rational direction in your lattice, and you take in this rational direction, you look what is the length of the shortest vector, and then it's like the height of this rational number, and then you sum over all rational numbers. You take 1 over that height raised to the power lambda plus 1. Hopefully I explained this well enough. So now, so similarly for SLN, you would be summing not over, so for SL2, we were summing over just one direction, that is one primitive vector in the lattice, or one rational direction, or one point in P1 over a field of rational numbers. For SLN, we sum over flags of linear subspaces. You sum over one-dimensional linear subspace contained in two-dimensional linear subspace, contains a three-dimensional linear subspace, and so forth. Over, well, in this case, I'm doing it over rationals. Now, each one of the subspaces will intersect my lattice in a lattice. And then the height, the analog of the length of the shortest vector, is just the determinant of that lattice. And so the value of my function, norm of lambda raised to the power lambda, that would be this product of determinants of this. So you have a, like I said, if you have a flag of rational subspaces, then it defines me a flag of sublattices, and the norms of this, and the norm of this flag of rational subspace is just the product of the determinant of this lattice raised to appropriate powers. So that's this means in this case the Eisenstein series is really just a height zeta function for rational points on the flag variety. So an object very very familiar, probably very dear to anybody who does kind of arithmetic geometry. And now if we're doing if we're in positive characteristic situation, then the situation is even closer to what people like to do in algebraic geometry. Namely, I need to evaluate some function on a point in Ban. A point in Ban is a G bundle over my curve C. So I have some curve C, which I have I've drawn here. This is C, and I have a G bundle over it, which I didn't draw. But associated to G bundle, I always have the associated G mod B bundle, which I can just take a G bundle modded out by B, or take the associated G mod B bundle, or take the bundle of flags in your original kind of bundle. And so that would be a bundle of, say, for SL2, this would be a bundle of P1s, or in general, the bundle of G mod B bundle. And then what you're counting sections of that bundle weighted by their degree. So the degree of a curve in the flag variety is the core lattice of your group. This is H2 of your flag variety is the core lattice of the group. And so this degree of a curve defines for you an element there, which you can pair with lambda. And so what you're summing this kind of generating function, which is very, very, very standard thing to consider in geometric geometry, where you kind of count all possible curves weighted by their degrees, or count maps and count sections of some bundle weighted by the sections of some fibration weighted by their degree. So that's that must be really familiar to many of you. So now, in general, Eisenstein series satisfy. This is again a hard result going back to Langlands, that they satisfy. Not only do they have analytic continuation, they have functional equation, which says that if I act by Weil group element on Eisenstein on the label lambda, then the resulting series is proportional to my original series. Therefore, the eigenvalues of Hecke operators, they're not just functions of lambda, they're symmetric functions of lambda, or W invariant functions of lambda. And moreover, if I'm in positive characteristic, then they only depend on Q to the lambda, which is therefore they're not only they're W invariant, but also they're 2 pi I over log Q periodic if characteristic is positive. And thus the spectrum that I'm looking for is abstractly a subset in the following quotient. So I either take we decided that the space of characters, with the space of characters for my group of diagonal matrices with positive real entries, that's the Langlands dual. That's the torus in the Langlands dual Lie algebra. So this capital L here stands for Langlands dual, and A is the maximal torus in my Lie group. My Lie group, and it's either if my characteristic 0, then I have to take the Lie algebra in the Langlands of the torus in the Langlands dual group, or if I'm in positive characteristics, I actually take the torus in the Langlands dual group. And so this by definition lives with bold-face lambda. And depending on these two cases, if characteristic is 0 or positive, the spectrum is a subset in either. I apologize. The spectrum is a subset either in this lambda mod, always in lambda mod W, but lambda again it means two different things. It's either maybe I'll say it one more time. It's either the maximal torus in the Langlands dual group, or is the Langlands-Zuul complex group. The Langlands-Zuul for us is always complex group, or it's the Lie algebra, depending whether you're in fields of zero or positive characteristic. Okay. And already, again, I keep referring to the influence of Langlands over the whole subject, and already is envisioned by him. Of course, he inspired, his vision inspired generations of people working on this thing. So it's not this kind of philosophy has been really been around. So is envisioned by Langlands. The spectrum, it has something to do with the Langlands-Dunn group, and specifically with the fact that the space where the spectrum is contained is this lambda mod W. Those are semi-simple conjugacy classes in either its Lie algebra, if I'm in characteristic 0, or in the group itself. Okay, because if I have a semi-simple conjugacy class, it's always conjugate to maximal torus, and in the maximal torus, it's furthermore you have to mod out by W. And it's in fact in terms of what you need from this Langlands dual group for this problem, you need the conjugacy classes of SL2 triples. So the conjugacy classes of homomorphisms from SL2C to the Langlands dual Lie algebra. And we will need to know what they're centralized. So the piece of data will be the pieces of the spectrum correspond to the homomorphism from SL2 triples in the Langlands dual Lie algebra. That is to say, homomorphism from SL2C to the Langlands dual Lie algebra. We will, from that homomorphism defines as its centralizers in the group. And for a given phi, we will denote by H the image of the diagonal matrix, and by E the image of the standard nilpotent matrix. So this is E runs over conjugacy classes of nilpotent elements in this Langlands dual Lie algebra, and H is its corresponding characteristic, what's called the characteristic of nilpotent conjugacy class. All right, so this is our main result. Maybe I cannot stress enough that it's but a step in a very long development of the subject, in which it goes back to Langlands, many great mathematicians participated, and I think Eric Obdam is. I saw him briefly in this call, and I think he and his collaborators have either have a almost complete alternative proof or complete alternative proof. So anyway, I think this is there's other ways to think about it, and Eric and his collaborators been making very good well. Anyway, so
yes,
the theorem says.
So, and thank you.
Yeah.
And yes, we are writing it now. Yeah.
Yeah. So right. Thanks, Eric. Great to hear you. So so this is the theorem says that this is the spectrum is always the image of either, if you're in positive characteristic, then you take the compact group of the centralizer of this. So you take the centralizer of this phi, which is some reductive group. You take its maximal compact subgroup, and you multiply it by q to this half of the characteristic. This defines you some subset in your group, and you take its image in the space of conjugacy classes at the spectrum. This is for positive characteristic, and for zero characteristic, it's exactly the same, except so the general rule, if you're in zero characteristic, you replace all groups by corresponding Lie algebras and the q by 1. And so where you had product, we get the sum. Where you had q to the h over 2, we get just h over 2. And then we get the Lie algebra of the compact group. And we also, so this decomposition also comes with explicit determination of the spectral measure and the spectral projectors, which I'll get to that in a second. And so in the rest of the talk, I'll try to explain how the proof goes. And the first step is again goes back to Langlands. Yeah, too bad Langlands is not on this call, so that'd be I hope he's he can, yeah, I don't know. It'd be probably fun for him to know how far his influence goes. So so the first step is the following. So maybe I'll backtrack in a second. So maybe when you have time, I can backtrack a little bit.
Andrei, I
So
think David has a question. Yeah, David, your hand is up, but you muted. No. Ah, okay. Sorry. I think it was just a mistake.
Yeah. So
I muted,
so
but it's not a question. It's my iPod plays games.
Sorry.
yeah. So we had two kinds of functions. Ones were this I don't know, kind of, Poincare series, if you'd like, where you had a smooth compactly supported function and you sum it over the orbit of the group. And so then, so this is one way to spend the span we want, and then the other are the Eisenstein series, which are by themselves are not in L2, but participate in a spectral decomposition. And so now let's look at this part here. And the relation between one or the other is the Mellin transform in the group. On the group of diagonal matters with positive real entries. And so now let's go back here. And so now what we would like to have a distribution on the space lambda. So lambda was the space of lambda is where the big lambda, the big fat lambda is where the label lambda lives. And this is where the Eisenstein the Eisenstein series are, their labels belong to that space. And also that's the spectrum. That is also the spectrum of Hecke operators. And now we would like to say that we would like to define a distribution which is on a pair of test functions, and the test functions we will take of the form that they're Mellin transform of smooth compactly supported functions. And the value of the distribution of pairs on the pair of these such test functions is given by their L2 product of the corresponding series with, people call them pseudo-Eisenstein series. So one is the Eisenstein series, the other is pseudo-Eisenstein series. One is the, one kind of thing is the Mellin transform of the other. And so when we take the L2 product of two pseudo-Eisenstein series, this will depend linearly on functions F1, F2, and we'll think of this as a distribution of lambda cross lambda. And Langlands gives a counter-integral formula for this distribution, and the traditional path to spectral decomposition went through contour shift and residue calculus in that formula. So that's this is the first step is, so this is where this is the step we also make following Langlands, but then after that there's some different path. And the different path is maybe this is now the reason why this is appropriate in algebraic geometry seminar, is that we find a topological algebra geometric description of this distribution as a certain equivariant genus. So that's kind of the main key point. I mean, the first key point here. And what is this and how does this work? So if I have, so generally, maybe for instance, classically considered for a smooth, compact, and stably complex manifold, then and they're defined by taking, if I have, let's say, a polynomial in one variable, then I can maybe, let's say, psi is a polynomial in one variable, then I can take the Chern roots of the tangent bundle as an argument of my polynomial, multiply them together. This gives me a cohomology class on my manifold, which I can then integrate. Right? For this to be defined, the integration, the manifold has to be proper. For the tangent bundle to exist, it has to be smooth. And for this tangent bundle to have Chern class, it has to be stably complex. So those are the kind of basic assumptions. So that is this map that goes from M and goes to psi of M. That's a map from manifolds to numbers. But in fact, it factors through the complex cobordism ring of manifolds, And so that's a kind of classical use of this genera. And this works also in the presence in the covariant situation. So if I have a compact group, so here H, boldface H already denotes a compact group. So previously we boldface letter referred to algebraic groups, but here just for ease to kind of usual topological convection, the group would be compact, and then the corresponding algebraic group will be its complexification, a complex reductive group. Anyway, so if I have an action of a compact group, then I can this also can be defined. It takes values, but now it takes values not in numbers, but in the covariant cohomology of a point. And the covariant cohomology of the point is a ring, which is whose spectrum, which is just H invariant polynomials on the Lie algebra of H, of the complexified Lie algebra of H. Those are this is the H equivariant cohomology of a point with complex coefficient. This is a ring, and that's just a ring of H invariant functions on the complexified Lie algebra of H. So this is for when psi is a polynomial, but of course this is you get a map of functions go to functions, and by continuity or by any other means, you can extend it to many more general functions. So that's what is so this is you get for instance, you can take a function if you have a function which is analytic in the neighborhood of the Lie algebra of the unitary. So if you think of polynomial psi was a polynomial in one variable, but polynomials in one variable in this language, we'll think of this as this one variable being the polynomial in one variable is one variable having to do with the group C star. So we think of this H, or maybe U1. So if you think of if H is U1, this equivariant cohomology of a point are the polynomials in one variable. And so then if we take if we have a function analytic in a suitable neighborhood of U1, the compact group here, then the corresponding genus will take functions analytic in a suitable neighborhood of the Lie algebra of the compact group. So that's the definition. Well, that's one step in the definition. And then exactly parallel construction work in equivariant topological K-theory. The only difference is that the spectrum of equivariant cohomology of a point doesn't look like the Lie algebra anymore. It looks like the group, because if I take H equivariant K-theory of a point, that is just the representation ring of the group H. What's the representation ring of the group H? Those are, if I say tensor with complex numbers, those are just H conjugation invariant regular function on the complexification of my group. So these are just, you take the complexified group HC is complex reductive group, you take regular functions on it, you take H invariant ones. That's the spectrum of the equivariant cohomology of a point. That's so the main difference between cohomology and K-theory is that in one case the equivariant cohomology of a point looks like a Lie algebra, in another case it looks like the group itself. So that's the main difference. And to unify these two situations, we will introduce notation, and suggestively we'll introduce this kind of boldface lambda subscript H. We will consider two situations. We'll consider in situation of cohomology, this would be the Lie algebra modular conjugation, and in particular in this case, the boldface lambda of U1 will be C. And then the other situation, you get the group modular conjugation. This is when the boldface lambda of U1 is C star. And so this denotes these are the spectra of the cohomology of point mod H in the corresponding cohomology theory. So there's one of them is the ordinary cohomology, another is one of the extraordinary cohomology topological K-theory. And this is to unify the notation. And the group, this boldface group lambda sub U1, which is either C or C star, that's the group law of the cohomology theory. So the cohomology theory, they usually construct it the other way. You start with the group law. Here we okay. And so central to our argument, which is the observation that this this genus can be defined for non-compact manifold as a distribution on lambda boldface lambda sub H. And this is of course in the representation theory that goes way back when people thought about characters, how to think about characters of infinite dimensional representation. They realized that of course that character need not converge, but maybe well defined as a distribution. And in the context, in this maybe more geometric context, maybe this was first noted by Atiyah, who noted that if you're certain operators which are not exactly elliptic, but close to elliptic, their indices are not functions; they're rather they're distributions. And this is the kind of situation we have here. So when the manifold is not compact, then the previous construction will naturally lead to distribution on the spectrum of a covariant cohomological point. And the algebraic. So for us, this is the important setting is the algebraic geometry setting, where the convenient definition for us to use is that of cohomologically proper space or cohomologically proper derived stacks and so on and so forth. So what is that? So if I have a quotient stack x mod boldface H, where H would be a linear algebraic group, but it's not assumed to be reductive. So it's important. This will be important for us to work with non-reductive groups. So this is called cohomologically proper if the following is true. So first of all, what's a coherent sheaf on this quotient? Coherent sheaf on the quotient is just H a covariant sheaf on a pre-quotient. And what does it mean to take its sections? It means I take well, actually, I apologize. Yeah, no, that's correct. So what does it mean to take its sections? It means you take its global sections as before, but you're only interested in H invariant sections. That's the functor function. The global sections for like a coherent sheaf, again, coherent sheaf is just H covariant sheaf, and global sections are H invariant global sections. And so then this map from x mod H to the point, this is cohomologically proper if this r pi star are 0 pi star, and all the higher derived functors, they all coherent for a coherent sheaf F. And the derived functor there will include both the cohomology of the sheaf itself and also the group cohomology if the group is not reductive. And so the requirement is that while if I have a coherent sheaf on my coherent sheaf of my quotient stack, I push it forward to a point, then all the push forward and all the higher derived push forward, they all cohere. That's the condition. And so and that's been already put to good use by people like Dan Halper-Leisner and others. So this seems like a good notion. I mean, this is notion sufficient for our purpose. Our goal with David is not to define some theory of some. It'd be good somebody to work out a good general theory of such object. Our goal is to have a theory that works in examples of interest to us. But so for us, this cohomological properness is a good notion. It suffices for our purposes. So maybe there's more general. So this is with this notion, one knows that the covariant general have a general extension as distribution to smooth cohomologically proper stacks, as well as many virtually smooth derived stacks. For us, again, we're not concerned with general derived stacks. For us, we work specific spaces, and for them, the only ingredients that come into the definition of the specific spaces are the Kazul, the Chevalier-Eilenberg, and the Czech complexes. So we don't think anything more general. But of course, like I said, it seems like a good geometric question to study this genera in the context of cohomologically proper virtually smooth derived stacks, or maybe some slightly even more general context. That seems like a very good question to, some very natural question to ask, but it's not what we're doing in this paper. We just use the natural extension of this genera to solve the problems that I stated at the beginning. And so now we go back to the spectral problem, and we know that if we make the following definition, then we get a kind of a certain unity of the two columns in this table. And what's the definition? Remember, from the very beginning, the definition of the Eisenstein series involved taking the norm. So you had an element in the adelic group, and we took its norm to get an element in real matrices. Okay. And so then the important thing for us is to let's just look at the image of the norm map. So this is the norm takes ideals to positive real numbers, and look at the image of that. And this image, what will be? This will be all of R plus if the field has characteristic 0, and it will be subgroup generated by Q if the field is of positive characteristic. And so if we look at the dual group to this Q, this blue Q, so this blue Q is the image of the norm map, and the dual group, meaning the home to C star, that would be lambda C star. In other words, so I claim that with this definition, we find that both in the situation of 0 characteristic and a positive characteristic, if we take the group, if we take the group law of the cohomology theory to be the dual of the group Q, then it's always the case that my space lambda, on which the spectral decomposition is supposed to happen, is always the covariant cohomology of the point for the Langlands, for the torus in the Langlands dual group. Okay, so it's not a complicated statement, but it's a useful statement because it opens. Maybe I'll repeat it one more time. So there are two cases in what we considered. One is fields of positive characteristic, one fields of 0 characteristic, and the way to quantify their difference is their image of the norm map are the two different subgroups of the positive real numbers. And if we take the dual groups of these images as the groups of cohomology theory, we'll get the ordinary cohomology and equivariant K theory respective. And the interpretation of this Eisenstein distribution, this capital psi i's, would be equivariant genus of a certain space in the cohomology theory that corresponds to my field, corresponds to characteristic of the field. All right. And speaking of the field, to bring in the field, what we will need to, we have to pick a specific genus, right? We need to, right now psi is like an arbitrary function. We need to pick a specific psi. And the specific psi we will take is the following. Consider a two-dimensional space, which convenient to write as a cotangent bundle to C1. So it's C2, but somehow it's good to think of this as a cotangent bundle to C1. And then we have an action of two-dimensional torus on this space. One will come from the action on C1 itself, and this on the C1 itself, it will act with the weight -1. So the variable x will be act with weight 1 over x on the base coordinate. And there, of course, the dual weight on the cotangent space will be x. And then whenever we have a cotangent space, we will make the generator Q of this group Q, the image of the norm map. We will act this with weight, again, -1. So this will act by 1 over Q in that direction. And if it's a Lie algebra case, then instead of taking the generator, we'll take the infinitesimal generator. This is the Q divided the Q in the Lie algebra. We'll still act with weight -1 there. And so then we would like to take such genus psi that the genus of this two-dimensional space equals the completed zeta function of the field F. Why did we need a two-dimensional space? It's because it's because the completed zeta function of a global field has two poles. And so this, if you want to interpret this topologically, these two poles will have to come from two different weights of some action. And so this would have to be something two-dimensional. This is why we'll in a minute we'll see not just the flag variety, but the cotangent bundle of the flag variety. So that's a way to get something from functions. This is a way to account for two poles in the completed zeta function. And why did we want this particular combination of the weights? Well, it's because of the functional equation that the function psi has to satisfy. So this psi can always be found by the fact that psi satisfies the functional equation. So in fact, there's always a Weierstrass type factorization of psi into two functions, such that then you take the genus of this two-dimensional thing is given by psi. And so now the spectral decomposition can be deduced from the two following results. First one is really a reinterpretation of Langland's formula, but I think maybe I would argue that it's convenient reinterpretation. It says that this distribution, that's in fact a genus of one particular space. Namely, it's T star of this double quotient of G by the Borel on the Langland's dual side. And as before, we make this group, I said that always we make the group, the script Q, we always make it act on all cotangent bundle by scaling the cotangent direction with weight -1. So this is how it acts. And we always evaluate on the generator of that group. So evaluate on this generator as an element Q or the Lie algebra element kind of Q divided Q in the characteristic zero case. And so what is and why is this a distribution lambda square? Well, because it's a quotient by two copies of the Borel, and the covariant cohomology of a point for a Borel is the same as the covariant cohomology of a point for the maximal torus. So this is a distribution on two copies of lambda, so as before. And if you think, what sort of space is this? Well, this is what's a cotangent bundle to a quotient. The cotangent bundle of a quotient involves the Kazul complex form a moment map equation. And also when we take the quotient, also since the quotient again is not by reductive group, there will be some Chevalier-Eilenberg complex for the unipotent radical of B. So it's not. So this is this is about the sense in which this is some kind of derived stack. But it's a very concrete one. So that's one part. And the second part is, let me try together. And the second part is that you can take that space and break into the pieces. So this is in the spectral decomposition, we would like to take this distribution psi and write it as a sum of spectral pieces. And you can do it not with the distribution itself, but the space itself. And the space, the way it's written, it may sound profound, but it's not. It's actually not so difficult to think that to imagine what it happens geometrically. Namely, if I have there's a cotangent to the group element. The cotangent to the group element is you can identify with Lie algebra element, and since it has to satisfy the moment map equation, it's a nilpotent element. And so this is how nilpotent elements come in. But anyway, this is your sum over nilpotent elements modulo the conjugation, and corresponding to this nilpotent element is a quotient. First of all, it's a quotient of some space, and you mod out by the centralizer of this nilpotent element in the Langland's dual group. And what's the space itself? You get two copies of the Springer fiber. The Springer fiber are the fixed point set of this E on the corresponding flag variety. So if you have on the Langland's dual group, I have the flag variety, namely G Langlands mod B Langlands. And it's fixed points. So E being an element, being an important element in the Lie algebra of G, it's a vector field. It acts on that space. It has its fixed locus called the Springer fiber. There you get two copies of that, and then you get the slice of the nilpotent element, but not actually the slice, but rather the Thom space associated with the embedding of the origin into that slice. So that's the decomposition. And I claim that this is a geometric form of a spectral decomposition, namely the group G compact in the spectral theorem that arises as a maximal compact subgroup of this group here. And integration along the Springer fibers here, that determines the spectral projectors, and the slice here together with the unipotent radical of the group that contributes to the spectral measure. And the way, maybe in a more practical way, the way this works is in practical terms. So what's the, maybe I'll write. So I took the previous thing, I removed the prefactor, and I rewrote it a little bit. So I took the quotient. So if I take a quotient by a general, some non-reductive group, I can write it as a quotient. I can take it in two steps. First, I take the quotient by the unipotent radical, and then I take the quotient by the reductive, by the Levy subgroup. And then I also abbreviated the G Langlands mod B Langlands for curly B. That's the flag variety for the Langlands dual group. And so this decomposition means that if I want to know the L2 norm of some pseudo Eisenstein series, that thing equals, first of all, there is an outside. Outside is a sum over conjugacy class of nilpotent elements. So this L2 norm will be a sum. So that says my spectral decomposition, first there'll be a direct sum decomposition. Then the next step is that here I have a quotient by reductive group. When I take a quotient by reductive group, that it's just, you take invariance with respect to reductive group. Taking invariance with respect to reductive group means you can integrate over maximal compact subgroup. And so this is how the maximal compact subgroup in the centralizer of E comes in, but the maximal compact subgroup in the centralizer of E is the same as the maximal compact subgroup in the centralizer of phi. So that's how the integral comes in. Now, what do we integrate? So there will be a certain weight that comes from the fact that this here is essentially a linear space. Well, never mind the Thom space, but this is a linear space and this is a linear space. This is some representation of this group. It has some weights, and then you take the values of psi on this weight, and you take the absolute value. That's the weight. It's like the spectral measure. And then finally, what do you integrate? You integrate the L2 norm of a certain operator, which is proportional to the projector. So I wrote the script P. P is strictly speaking not the projector, it's proportional to the projector. And the way it's defined is defined as the following composition. What was F? F was some function the way we interpret it in the first in the first theorem, or maybe theorem 2, I call it, that we have identified the test functions with K-theory classes on the flag variety. So F is a K-theory class on a flag variety. Of course, we can restrict it to the Springer fiber. We can restrict to the fixed point set of E, and then we can tensor it with the corresponding genus and integrate, and we're going to get to the K-theory of a point of G-Langlands dual group. So this is going to be the integrand here, but concretely this integral here, this integration is just summation over some subset of a Weyl group. So you sum. So this is, in other words, this is what you get a sum of integrals where the integral is over maximal compact in the centralizer, and what you're integrating, there is a certain density, and then there's certain projectors which are just have to do with summation over Weyl group. Okay, so this is now I'm maybe at 1 minute, and have a slide that says further directions. And what can I say about further directions? You can, well, first of all, it's only have 1 minute left, and maybe that minute is gone already. But second, you can ask, is this some kind of one of the, kind of miraculous coincidences that sometimes happen in number theory. That just happens that some numbers equal some other number. And in fact, it isn't. So meaning, if you look at every, the many pieces in the puzzle I described, maybe not, certainly many. There was the part about, well, and all of these pieces are in fact movable. So with David, we've been exploring many directions, and in all of these directions you can move. I mean, you can I talked about unramified case, you can do the ramified case. I talked about minimal parabolic, maybe you can also, I think it's one can imagine doing other parabolic. I talked about the flag variety. I think one can imagine doing many other varieties. And anyway, so it seems to me that like I said, this picture moves in many different directions, and maybe this is the sign that David and I, maybe we have kind of many ideas how it can be moved, but maybe we're still searching for one big overarching idea. We landed in some point in the space of ideas, and we can see that we can go in this direction, that direction, but maybe we don't have an overarching idea which will encompass all the different ways in which one can move from this particular point. But it's maybe well, first of all, I'm over time, and anyway, whatever I can say about the further direction, that will certainly require another talk. So maybe I'll stop here, and thank you for your attention.
Thank you, Andrei, very much. Let's thanks Andrei, and in Zoom as well. Okay, let me stop the recording, and now